Alrighty, well, like I say in the Schoology, that these two pages, pages 13 and 14, are optional. However, there's a lot of good Punnett square practice here, and there's lots of things to learn about genetics, and so let's go through a couple of like the highlights and what have you. All right, let's look at 1A. So it says a homozygous, right, purple plant. So that would be a big P, because it's homozygous, and purple right here is dominant. And a homozygous white. Now, I suppose I didn't even have to tell you that. It could have just said it was white. And the reason is because in order to be recessive, remember, you have to be homozygous. So therefore, little p, little p. So we have big P, little p, and we get all heterozygous F1 generation. So what's the genotypic ratio? They're all big P, little p. They're all purple flowered because big P would mask the little p. And that's that. So use a Punnett square now to cross those. Well, we have heterozygous. So 50% of the time a big P, 50% of the time a little p, right? Because this would be one of the parents, or this one, or this one, or this one. Again, big P or a little p. So what do we end up with here in the F2? We end up with one big P, two big P, little p's, and one little p. Now, phenotypically means, what does it actually look like? Well, that one would be purple, 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 and that one would be white. So 3-1. Use a Punnett square to show a cross between a heterozygous yellow. So big Y, little y. Why? Because up here it says yellow is the dominant trait for pea color, and recessive is green. Farmers like that. Why do they like that? Because we want to buy green peas, right? Well, a farmer knows that if he crosses a green pea plant with a green pea plant, recessive times the recessive, 100% of the time he's going to get recessive. But back to the problem. So when we cross a heterozygous with a homozygous recessive, otherwise known again as a test cross, right? Heterozygous times homozygous recessive is a test cross. We get two big Y, little y's, and two little y, little y's. So that's what you see there. Two yellow for two green, because these would be yellow and those would be green. If you put 1-1, you wouldn't be necessarily wrong. All right, a dog's phenotype. Don't overthink these. A dog's phenotype can be determined by just simply looking at the dog. The genotype's a little more difficult. We'd have to do some genetic testing to figure out the dog's genetics. And then the last thing talks about this thing called cystic fibrosis. Real quickly, what cystic fibrosis is a disorder that causes an excessive amount of mucus to build up inside of the lungs of an individual. Guys, and I mean, it's really excessive to the point where like it's almost like the person is like almost like drowning in their own mucus. It's pretty tough. Okay. So here it says 1 out of every 20 Caucasian Americans has a recessive allele. That doesn't mean they have it. It means they carry it. So let's see. So it says, describe why there is such a large difference between those who carry the allele and the number that are actually born with it. Well, what ends up happening is, if we have something like this, let's go back up to our big P, little p. If we had a 1 out of 20 carrier marrying another 1 out of 20 carrier, only 1 out of those 4 offspring would actually get it. And so the same thing down here, right? It takes 2 little f's. That's what this says down here at the bottom. It says it takes 2 little f's to get cystic fibrosis because it's recessive. And so what ends up happening is for 1 F, it would be 1 out of 20. And then you would need 2 people who are 1 out of 20. So 1 out of 20 times 1 out of 20 is roughly, off the top of my head, 1 out of 400, I think. So the reality is that or no, that'd be even less than that. Oh, it's right here. We have 1 out of every 2,000 babies is born with the disorder. So long story short, that's why cystic fibrosis, okay, can be carried, but it doesn't show up that often. It's a 3-1 ratio. Alrighty. I hope you learned something from these pages. Alrighty, we have a thinking problem for number 5. So number 5 says 2 white mice, okay, and let mate, and the F1 generation all have white coats. So good for that, okay, so whites gave white. One of the daughters of the F1 generation mates with a brown male mouse, and their offspring all have brown coats. The white generation is most likely what? Well, just like we talked about with the peas just now, if we have a recessive mating with a recessive, like it's talked about in this very first sentence right here, then what's going to happen is we're going to get recessive offspring every time. So that's that green pea plant times a green pea plant giving a green pea plant. Here it was white mice, okay? Now, what ended up happening though here is the brown masked the white when we took the two traits and put them together. Therefore, what I would say is the answer to the problem is that these F1 generation, these white ones, well, they were just recessives mating with other recessives. And so letter A is the best answer. Okay, so what we end up with is for each generation, the very first P generation, the parents, would have been a white times a white. Now notice I used little b's, and the reason for that is because brown is the dominant, right? And we always take the letter of the dominant trait. So little b is actually white, little b is white. Now here we had that white male, or white, right? It says the F1 generation mates with a brown male. So here's your white one again, okay? But here's a brown one. And the reason I would say it's homozygous dominant, big B, is because up here it said all their offspring have brown coats. And so this would give all brown, and they'd be heterozygous. Now, number 6. So if you have a child, right? Every single time that you have a child, your chances of having a boy is 1 out of 2 or 50%. And your chance of having a girl is 1 out of 2 or 50%. And it doesn't matter how many kids you have, folks. You can have 4 girls in a row and be having a 5th child. And the 5th child's chances of being a boy or a girl is still 1 out of 2 or 50%. Like every time it's 50%. So it says if a couple has 4 children, what is the chance that 2 will be boys? What are the chance 2 will be girls? Well, the chances are always 1/2, okay? So we have 4 kids right here. The chances of them having 2 boys and 2 girls, right, would be 1 out of 16. 1/2, 1/2, 1/2, 1/2. All right, show a cross between these are dihybrid crosses, these last two. So remember, with dihybrid crosses, we're doing that foil thing, right? So we have a homozygous purple and yellow peas. So homozygous meaning the letters are the same, okay? With a pea plant that is white flowers and green peas. So again, homozygous recessive. We didn't have to tell you that because by being white, you had to be homozygous. By being green, had to be homozygous. And it's called a dihybrid cross again. Here is your Punnett square that shows up from that. And you're going to give the genotypic ratios. Well, because you have homozygous times homozygous, every organism in here is going to be heterozygous for both traits. So they're all big P, big Y, little y right here. Now, what would this look like? Well, big P, little p are all going to be purple. Big Y, little y are all going to be yellow. Therefore, all purple and yellow. A little different down in here with the guinea pigs. So rough coat is dominant to smooth, and black is dominant to white. So it says we take a heterozygous for both right here, and we make that with, okay, let's see. Oh, another one that is also that. So heterozygous times heterozygous. And you can see here, heterozygous times heterozygous. And so what we end up with is we end up with a lot of genotypes. But like we talked about in that video a couple of days ago, anytime we have a dihybrid cross with heterozygous times heterozygous, we get a 9 to 3.